In July 2025, Google's threat intelligence team saw something they could not explain. Attackers were preparing to use a zero-day. The signs were there: staging activity, preparation. But they could not work out which flaw the attackers had found. They knew a door was about to be opened. They did not know which door. So they handed what little they had to an AI agent called Big Sleep and asked it to look. It found the flaw, a critical bug in SQLite, one of the most widely used database engines on Earth. A bug that, at that moment, only the attackers knew about. It was fixed before it could be used. Google believes that was the first time an AI agent directly stopped a real attack from happening. Not detected it afterwards, stopped it. So how does that work? How does a machine read code it has never seen and find something human reviewers missed? That is what this video is about. No hype, just the mechanics. First, clear away the picture most people have. When people hear AI hacking, they imagine software smashing through a firewall like a battering ram, something violent and fast. It is nothing like that. It is closer to automated research, patient, methodical, and mostly boring to watch. What these systems do is read source code, compiled binaries, network responses, error messages, crash logs. Then they form a theory about where something is weak and they test it. They combine four things that used to live in separate tools: a language model for reasoning and planning, static analysis for inspecting code without running it, dynamic analysis for watching a program while it runs, and machine learning for spotting patterns across enormous amounts of data. Together, that does parts of the job normally done by penetration testers and security analysts. Not better than the best humans, but faster, cheaper, and at a scale no team can match. An autonomous security agent is not one model doing everything. It is a model with hands. At the center sits the language model, acting as the planner. It gets a task. Examine this application, find where it is weak. It breaks that down. What is this built on? Where are the entry points? How is user input handled? But it cannot reach into a system by thinking about it. It needs tools, so it is given some. Network scanners, code analyzers, debuggers, a terminal. The model asks a tool for something and the tool answers with real data. Which ports are open? Port 80, port 443, port 22, and the model interprets that. 80 and 443 mean a web server. 22 means remote login. That changes what is worth trying next. Now the part that matters most. The loop: plan, act, observe, revise. If a command fails, it reads the error and adjusts. If a script crashes, it rewrites it. If one route is blocked, it finds another. That loop is the whole difference. A traditional scanner runs a fixed list and stops when the list runs out. An agent keeps going because it is not following a list. It is pursuing a goal, which is also why these systems are hard to contain. You cannot predict every route something takes when it can invent new ones. So how does it actually find a vulnerability? A vulnerability is a flaw that lets someone break a rule the software was meant to enforce. There are two ways to hunt for them, and modern systems use both. The first is reading code without running it. Static analysis. Some patterns are known to be dangerous. In older C code, certain functions copy data without checking whether it fits. Supply something longer than expected, and the extra spills into memory it should never touch. Spotting that is the easy part. The real question is whether an attacker controls that input, so it traces it. It takes something untrusted, a username, an uploaded file, and follows it through the program, checking whether it reaches anything sensitive without being validated first. That is taint analysis, and it is where the reasoning genuinely helps, because following one value through thousands of lines is exactly the tedious work models are good at. The second approach is to run the program and watch it break. Fuzzing. Fuzzing means feeding a program deliberately malformed input to see if it falls over. Traditional fuzzers throw huge quantities of random data at a target and hope. Guided fuzzers watch which parts of the program each input reaches. If an input touches code nothing else has touched, that input is interesting. Keep it. Change it slightly. Try again. Over thousands of cycles, the system works into corners nobody has tested, because nobody thought to send that shape of nonsense. Finding a crash is not the same as finding something dangerous. Most crashes are just bugs. The next question is whether it can be turned into control. When a program crashes, an agent examines the wreckage and asks what a human expert would ask. How much of this did the attacker control? Can it reach something that changes what the program does next? Can it be triggered remotely, or does it need access you already have? None of that is new thinking. What is new is that a machine works through it on thousands of crashes, while a human team gets through 10. And there is a line here worth naming. Proving a problem exists is not the same as exploiting it. A defensive system confirms the flaw is real, then stops and writes up the fix. That distinction is the whole difference between security research and an attack. Put that together and you get autonomous penetration testing. A penetration test is a controlled, authorized simulation of an attack. You hire someone to break in so you learn what is weak before somebody hostile does. An agent runs the same sequence. It looks around, finding machines and services. Then it works out detail. What operating system, what software version, anything misconfigured. Then it cross-references. There is a public catalog of known security flaws, and if a system runs a version with a known problem, that match is instant. Better systems describe what they did using vocabulary the industry already agreed on, from the MITRE ATT and CK framework. It sorts attacker behavior into tactics, the goal, like getting in, gaining higher privileges, or moving sideways through a network, with specific techniques underneath each. That turns the output into a story. Not you have a problem, but here is the path someone would take through your network and where it would have been stopped. And this is real now. In June 2025, an autonomous system called XBO became the first to reach the top of HackerOne's leaderboard in the United States, competing against human researchers. Just over 1,000 reports in about 90 days, 54 rated critical, a machine placing first in a field of professionals. Here is the part that gets less attention and it might matter more. The same capability works on defense. If you run a large environment, your problem is not a lack of information. It is drowning in it. Firewall logs, endpoint alerts, login events, cloud audit trails, far more than any team can read. That gap between how many alerts arrive and how many people you have to read them is the actual security problem in most organizations and has been for years. An agent can work through it. It can spot beaconing, malware quietly checking in with its command server at regular intervals, which looks like nothing in isolation, but forms an obvious rhythm across thousands of events. It can learn what normal looks like for an account and notice when that account stops behaving like itself, reaching for files it has never touched, logging in from somewhere it could not physically be. And some systems now act alone. Disable the account, cut the machine off the network, same loop, same reasoning, opposite purpose. Let's separate what has genuinely happened from what gets claimed. Go back to Big Sleep. Before the story we opened with, it had already done something notable. In 2024, it found a memory flaw in SQLite that nobody knew about in code that had not been publicly released yet, reported and fixed the same day. No user was ever exposed. That mattered because SQLite is not obscure or neglected. It is in your phone, your browser, and countless devices, and it is tested heavily. Finding something new in it is hard. Then there is the AI Cyber Challenge, run by DARPA, the research agency of the United States Defense Department. 2 years, finishing in August 2025. The task was not to build attack tools. Teams had to build systems that could find vulnerabilities in real open-source software, prove them, and write a working patch automatically. A team led out of Georgia Tech, with Samsung Research and 2 Korean universities, took first place and $4 million. Across the competition, the systems found 70 planted vulnerabilities. They also found 18 genuine flaws in real software that nobody knew existed. That is the number worth remembering. 18 real problems in software people depend on, found by machines and patched. Now the honest limits, because they are real. These systems are confidently wrong on a regular basis. A model can read code, build a completely plausible account of a vulnerability, and be describing something that cannot actually be triggered. Every finding still needs proving. Volume without verification moves the workload rather than removing it. Second, they cannot hold everything at once. Serious code bases run to millions of lines. A model working through one component has no view of how the whole system fits together. And some of the worst vulnerabilities live precisely in the gaps between components, not inside any one of them. Third and most interesting, the analyzer can be attacked too. If a system reads untrusted material, that material is an input, and inputs can be hostile. A comment planted in source code to steer an automated reviewer away from the interesting part. Instructions hidden in content the model was only supposed to read, which is the same class of weakness as everything else in this video. Something reads input it trusts too much and behaves in a way its designers did not intend. An uncomfortable thought. We are increasingly defending systems with tools vulnerable to the exact category of problem they exist to find. So where does this land? There is no separate attacking AI and defending AI. It is one capability. Read the system, form a theory, test it, adjust. Whether that is an attack or an assessment depends on who is running it and whether they had permission. So the question is not whether AI can hack. It clearly can. The question is who is pointing it and at what. And if you run infrastructure, the practical answer has changed less than you might expect. These systems are very good at finding ordinary weaknesses quickly. Weak credentials, missing patches, services exposed that should not be, the unglamorous things that have been on every checklist for 20 years. What has changed is the time you have. Those weaknesses used to sit unnoticed because finding them took human hours nobody had. That excuse is gone. Assume anything obvious will be found and found soon. If you want to see this go wrong in practice, I have covered 2 real incidents on this channel. One where AI models reached the live systems of 3 real companies. One where a model broke out of the environment it was sealed inside. Both make more sense once you understand the loop. So where do you land? Is this the best thing to happen to defense in a decade, or will attackers get more out of it? Tell me in the comments. I read them all. That's Modern Tech Studio. For informative videos like this, like, subscribe, and hit the bell icon. See you in the next video.